a permutation is a cycle or product of disjoint cycle. So we do this by the example. First we know what is the definition of permutation. Permutation is a 1-1 onto mapping from a set S to S, where you can say alpha is 1-1 onto. Now let S is equal to 1, 2, 3, 4. We define on 4 elements. So alpha we write 1, 2, 3, 4, and here we write the image A1, A2, A3, A4. Right? A1, A2, A3, A4 are image of 1, 2, 3, 4, and actually because the function is S to S, that means they are not different from 1, 2, 3, 4. That means A1, A2, A3, A4 belong to S because they are the image and they can take value 1, 2, 3, 4, right? So in case if alpha 1 take 1, A1 take 1, A2 take 2, A3 take 3, if we suppose like this, if A1 is 1 and A2 is equal to 2, A3 is equal to 3, A4 is equal to 4. Alpha is defined if I suppose the values, corresponding values of A1, A2, A3 and A4, because it is still 1, 1 and onto. Both conditions are satisfied, and in that case alpha become 1, 2, 3, 4, and because A1 is 1 and A2 is 2 and this is 3, this is 4, so it become identity permutation, and we write it like this, or also sometime we write like this. So we leave this case that A1 is 1. So we discuss the another case. If that means, so identity case we leave, we take let A1 is equal to 2, then this become 2, this become 2, and now we decide this. So this can be now A1 is 2, then what is possibility left for A2? A2 can be 1, 3 and 4 because A1 already has been selected. That means the possibility left for A2, these 3 elements. If I take, if A2 is equal to 1, then alpha is what? Then alpha become 1, 2, 3, 4. This we already take 2 and this become 1 and this remains still A3 and this A4. So here we notice that one cycle is completed. That means this cycle completed, 1 goes to 2, 2 goes to 1. So simply we can say 1 goes to 2 and 2 goes to 1. So one cycle is completed. Now we deal with the next element. That means we start from 3. From 3, now what choice is left for A3? Now A3 can be, because 1 and 2 already been selected, now either A3 is 3 or 4, but we don't take A3 is equal to 3 because then the case become of identity, and which we already have discussed. So I take A3 is equal to 4, and obviously if this element selected, and this selected, so what is left for A4? A4 remain, only possible is 3, and in this case alpha become 1 2 2 1 and 3, this is 4 and this 4 is equal to 3. That means we can write it 1 1 2, this one cycle, and this is 3 4. That means 3 goes to 4 and 4 come back to 3. So this is the product of two disjoint cycle. So hence alpha is product of disjoint cycles. Again we come to the point that if we don't choose A1 is equal to this, but A2 we don't choose. Now we come here again. If A2 is not 1, then what is the possibility for A2? If A2 is not 1 and 2 already have been selected, then A2 is equal to 3 or 4. Because A1, 2 is already fixed and A2 is not 1, then the possibility for A2 is are left out 3 and 4. So take A2 is equal to 3. In this case, this alpha become, that means this case alpha become 1, this is already 2 and 2, because A2 we took 3 and this 3, this is A3. So now what about A3? A3 we take what is actually possibility. Either we can say A3 is equal to 1 or 4. These two choices. So if I take 1, then this 4, because the 3 element already chosen, so possibility for left is 4, and in this case this become 1 2 3 and 4, and this is identity, so we need not to write it, and this become 1 2 3, and this is a cycle. But if I take A3 equal to 4, if A3 I take equal to 4, then alpha become 1 and A2 is 2, and A2 we are taking 3 and 3 I take now A3 I have taken 4. Now what choice for? So these things you have to remember, this and this we have selected. So what is left for A4? A4 definitely, because only one element is left, that is 3. That is 1. And in this case what happened? 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, and this become the cycle 1 2 3 4. That means 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 return 1. So this is cycle. Hence alpha is a cycle. So in this way we can understand the example. But in the same pattern, if I extend S is a finite set up to n, the alpha is same 1 1 1 2, and in this case how we can define? Actually here, because I take independent choice, I don't want to start from 1, so I rename the elements of S. What is the rename? I say these elements are A1, A2, A3. That means I take some element, the element of this I take A1, A2. So I don't know, arbitrarily I pick some number. So choose some A1. So A1 obviously in these n numbers belong to S. And what is S? S is 1, 2 up to n. Now obviously alpha is defined, then A1 has some image in S. Then we say that A2 is the image of A1. That means alpha A1 is equal to A2. Similarly, A2 also has some image. Take A3 is the image of A2, and this A2 is equal to alpha, so this become alpha into alpha A1, and this we can write alpha square A1. So keep continuing like this. Again, this A3 also has some image. That means if we continue in this way, until we arrive back to the first element, and there will be, we arrive, that means A1 is equal to alpha m A1. If we keep going, because the number of elements are finite, so definitely there exists some m such that we arrive back to A1. That means we return to A1. We know such m will exist because here we see that a sequence is, because the sequence A1 alpha A1 alpha square A1 is finite. Why it is finite? Because number of elements in S, and all these elements fall in S, and number of elements in S are finite, so this sequence also be finite. So if we keep continue, then the repetition will start. Otherwise a rotation or repetition will start. That means what repetition? These values start appearing again. Say alpha I of A1 is equal to alpha j A1 for some I and j with I less than j. Therefore A1 is equal to this is alpha A1, where m equal to j minus y. So I rub this. We express this relationship. Okay, this is long, so I have to rub all. We express this relationship among A1, A2, AM. In this process, if this process goes up to m equal to n, that means all elements of S are covered. Then alpha is a cycle, and if m is less than 1 and if m less than n, then we again start by choosing some new element B1 such that B2 is equal to alpha B1 and B3 is equal to alpha B2, and this we can write alpha square B1 and so on. We continue and this process till we arrive B1 is equal to alpha k B1. So on the same argument, so on the same argument, such k exist if all elements of S are exhausted, then alpha is equal to A1, A2, AM and B1, B2, BK, and these are two disjoint cycles. So we can say hence alpha is product of two disjoint cycles. Otherwise, if the elements not exhausted, then we start again by selecting C. If not all elements of S exhausted, then again we start by choosing some C1 from S such that C2 is equal to alpha C1, C3 is equal to alpha C2, and that is equal to alpha square C1. Continue till we arrive C1 is equal to alpha T C1, and if all elements of S exhausted, then alpha is equal to A1, A2, AM, B1, B2, BK, C1, C2 up to CT. So I hope you get the idea. Otherwise, if all exhausted, then this is, otherwise we proceed again by choosing some d1 and keep continue the all elements of S exhausted. Thus we write alpha as a cycle or product of disjoint cycles.